Here we go. This is the recap of the face-to-face ISA lecture. Um, After we tackled, what do we call it, the storage, and that's it. I'm not going to talk about caching and memory anymore. You'll see those in more details in the microprocessor course next year, normally. And now we're gonna focus on the CPU. All right, and the CPU gets the instructions from the right. So the language of the CPU is ISA, and you would remember that from now on using this meme, right? So the language of the CPU speaks nothing but the ISA, and the acronym ISA stands for Instruction Set Architecture, and you can also call it just architecture, and this could be seen as the dictionary of instructions that is supported by the CPU. The CPU sometimes, and for those who are following the OS course with me as well, we've seen that one of the reasons to terminate the process is the fact that it's trying to execute an instruction that is not defined. So how would we know that it's not defined? Well, the CPU is not understanding it, hence it's not part of the ISA, right? So it's not in the dictionary of the instructions that is understandable and understood by the CPU. All right, and you're gonna see out there that there's another term that is widely used, which is microarchitecture, and there's a difference between architecture and microarchitecture for you computer architects from now on. Well, microarchitecture is the actual implementation of the ISA, right? So this is how you get the tangible thing that you can put your hands on, and the microarchitecture architecture deals with concepts about the implementation of the ISA itself. And one of the concepts that we're gonna see this year is pipelining, for instance. All right, so yeah, so we know what ISA now is, and we want to know what machine code is. And your colleagues in the face-to-face lecture answered correctly that machine code is nothing but a bunch of ones and zeros that run on the actual hardware, as inputs and are delivered as outputs from the different components of the hardware, and which is completely true. However, what I wanna try and get is the relationship between the two. Well, there's a hint here. So let's see. If we're sitting on the hardware level, we're seeing a bunch of ones and zeros, right? If we're sitting here at the system software level, let's say we're at the kernel, well, the last thing that we'll be seeing is extremely, complex uh, characters that represent whatever has been coded on the application level or anything that the hardware is supposed to run. Well, actually, the OS or the kernel, the last thing that it sees is the ISA. And the ISA, as we've seen in the previous slide, it's the language of the CPU. So the ISA is at the same time the things that the CPU understands and the things that are used by the software to dictate what this CPU is supposed to do. Fair enough? And how does the CPU understand this? Well, using machine code. So if we look at it from this way, well, ISA and machine code are nothing but two sides of the same coin. Fair enough? Yeah, as I love to say it and say it over and over again, ISA is the boundary between system and software, between system software and hardware, sorry. And to me, this is my own personal opinion, and this is how I like to see it. ISA is neither really the hardware nor really the software. It's both hardware and software at the same time, and we're gonna find out why later. So yeah, this is awesome. Now we know the relationship between the two, which is basically the same thing. It's an alter ego. So what about assembly code? We've heard a lot of a lot of times assembly code. So first off, you already know that assembly code is in no way application. This is not what you not anymore anyways. This is not what you use when you're gonna create your programs. Fair enough, because you use like object oriented or really high level programming languages, and then there are a bunch of things that happen, maybe some compilation stuff like that, and you're gonna end up with the assembly code that will run on the hardware. Some might say that assembly code is definitely, and it's correct, related to machine code. Well, now that we know that machine code is nothing but the ISA, so assembly is extremely related to the ISA. Well, assembly is nothing but the ISA itself plus some extra pseudo instructions. So assembly is the last rampart of what's understandable by the humans, including the ISA, because we're looking at it from here, right? So assembly is ISA, so the architecture, plus some additional pseudo instructions. Pseudo instructions. Alright, and why bother include pseudo instructions to the ISA? Well, remember, assembly is the last human readable part of the layers, so maybe it's too complicated to code everything in ISA. It will take too long. Maybe it will be easier to have some kind of pseudo instructions that could be then interpreted or divided into the actual ISA instructions. So one extra instruction that will cover for 3 ISA instructions, and it will make the human being a little bit happier. That's a weird face, but anyways. Now the question is, who gets to understand that particular instruction and divide it into the 3? Well, someone said that maybe it's in the name. Maybe it is the assembler. Fair enough? Right, so here comes the fun part now. When we're gonna create an architecture, so I'm gonna use a MIPS as. Alright, so now we said that the. Alright, now comes the time of the binary interpretation of whatever they want to read. And by they, I mean the processors or the architectures. So let me get a pen here. Right, so see, now if for instance I'm having, let's say, a binary number which is 1010. Fair enough. Usually what they taught you till now is you're gonna read them in that direction, so the powers will get bigger and bigger. The powers of 2 will get bigger and bigger when you go from this way to that way. So here, for instance, to know the decimal value of whatever binary number that you have here, in this case is this one, well, all you have to do is do 2 to the power of 0 times 0 plus 2 to the power of 1 times 1, so plus 2. Then here, same these, 2 to the power of 2, I have nothing at all. Then 2 to the power of 3 here, which is 8 times 2 to the power of 3 times 1, and you're gonna end up with a number which is 9. Fair enough? This is the direction will result in that. What if, and bear with me for a second, if instead of reading it that way, you read it that way? Alright? Well, would it be the same value? Well, no, because you will have here 1, right? And then you will have 4, so the result will be 5. So let's, if I want to make a long story short, the little endian is the things that you learned until now, and big endian is equivalent to what I showed you here. It's the opposite. Well, the beauty of it, don't get confused, instead of dealing with the bits at the bits level, we're gonna deal at the byte level. So if we have a bunch of bytes that correspond to some number, so if we're reading it the normal way that you've learned to read it from now, so this should be the smallest byte, then a little bit more, this is the least significant, and a little bit more significant, a little bit more significant, and then the most significant one would be that one. And this is the normal direction that you read them. And this is little endian. Now if you read the bytes that way, well, you're gonna go big endian. However, the beauty of it, the bits within the bytes are always little endian, right? So it's all about the order of the bytes that you read them in. I'm gonna give you an example that would be way easier. So let's go for it. See, that number has 4 bytes. Bytes here, 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 and here. If you read it the little endian way, so if you start with that one being the smallest all the way to the biggest, what would be the value of it? Well, it's all zeros, and then you have the power of 2, whatever the power of 2 here. So it's 0, 1, 2, 3, 4, 5, 6, 7, right? And then 8 till 15, now 16, 18, 19, 20, 21, 22, 23, and this is 24. So 2 to the power of 24. And if the math is correct, let me double check it real quick. I'm having fun with you. So 24, and the result is correct. Yep, so this is the result here. And then if we interpret it the other way now, the big endian way, instead of reading that byte first, well, we're gonna start by reading that byte first. So it will be 2 to the power of 0 times 1, and that's it. So 2 to the power of 0, that would be 1. We good? What about MIPS? Well, MIPS is actually flexible, so it's considered to be bi. Hence, you need to specify whether you want it to interpret it as big endian or little endian. Right, now comes the slide of we're gonna talk about the operands, the size of the operands, and using the size we will be able to know what are the different types that we can represent, right? So with 8 bits we can represent all the characters in the ASCII code here. So we have 2 to the power of 8 possible combinations, characters, right? However, would that be sufficient to represent big numbers of integers, for instance? Most probably not, because we want to go beyond 2 to the power of 8, right? Unicode character as well, it's 16 bits, and as I told you before, from now on, when we're gonna say word, well, the size of the word is systematically 32 bits. Hence, half a word will be 16 bits, and a double word will be 64 bits, right? So here with 16 bits, we are covering more characters than we could cover in the ASCII code. Right? So Unicode is more inclusive than the ASCII code. Comes the integer. So this is 32 bits, 4 bytes, and then double word or long integer, that will be 64 bits. So it's 2 times a word. And forget about floating point. I don't really care, just for info. Right, so yeah, what are the things that we can do, the different operations when it comes to the ISA, especially the MIPS one as an example? Well, we can transfer data between the registers and the memory, between the registers themselves. Well, we can have something in the ALU, so the mathematical and logical operations. We could deal with floating point, but I'm not covering it this year. And then, most importantly, we can control the flow of our execution. So instead of having systematically sequential execution one after the other, well, we could have some branching or some jumps, or we can call some functions. So a procedure is a function, right? And this is what we're gonna see later on. And these are the bunch of operations and control that we can have with MIPS, and you can notice the red ones, for instance, and the black ones and the green ones. So notice the add ones, they are R-type, so they are strictly exclusively register instructions. And then you have the I-type, which are the immediate values. Remember, when one part is stemming from one of the registers, one source register, and then you'll have to add yourself the immediate value. And then you have some kind of jumps, so we can go from one place to another instead of having sequential execution. Where are my memory operations? Can anyone spot them at all? Oh, alright, I see them now. So the most common ones are LB for load byte and load word, and apparently they're considered to be I, so immediate. How come? Well, if you remember quite well from the previous slides, well, if I wanted to load something, I need to specify the destination register for sure. Then I need to specify the register that contains the base, the value of the base, so the base register. And then the offset, it was an immediate value, it was a number that we write ourselves. So hence, this is why it's a I-type. Right, so remember when we needed to figure out whether the instruction should be flexible or, flexible in the sense of variable size, or they should be fixed. Well, the MIPS people decided to fix the length of their instructions, and they fixed them to 32 bits. Now, 32-bit instruction, this means that it is something that is the same everywhere, hence usually it should make things faster, and we're gonna find out why later. So the instruction is divided into many things. Hold on, so I wanna know how many bits I need to represent my registers. So I had 32 registers, so I can go anything between 0 and 31 in order to represent those in bits. Well, how many bits are needed? 4. I will have 16, and 5 bits I should have 32. So yeah, with 5 bits I should be covering all the registers that I decided to have in my MIPS ISA. And let's see, it is true. So apparently we have 5 bits for the source register, RS, another 5 bits to specify the other source register, source register, especially in R-type, exclusively for R-type instructions. And what would the RD be then? Well, another 5 bits to specify the destination register. Here I have a field that is called OP. Well, most probably OP will stand for operation, right? Or this particular code is called opcode. And if we look at it for a second here, apparently we're having 6 bits. So from a purely theoretical point of view, with 6 bits, how many instructions can I have? Right, with 6 bits, well, all I have to do is do 2 to the power of 6. I'll have the number of instructions that are contained in the ISA. But then again, I can see that I could have more instructions in a way or another using other different fields that I did not use till now. But that's not the big question. The big question that I'm asking you, if I'm not using a R-type instruction, so I don't need another resource. Imagine that I'm using an I-type instruction, and an I-type, remember, one of the things I'll be reading is from this source register, and then in case of an addition, for instance, I'm gonna add myself the value here. So something that I write. So what if I don't want to stop? Imagine with only 5 bits here, well, I'll be stopping at 2 to the power of 532. So the maximum value, immediate value that I can add is 31. So it's 32 minus 0. Right? I don't want that. I want more. I want to be able to reach more values here. So yeah, I need a longer field. Let's take the whole thing here. What should I do? Let's see in the next slide. Yep. So apparently, this is what we've seen for the R-type. Now for the I-type, I'm still having my source register, and I have now more bits to represent my immediate. So my immediates, they go from 0 to 15. So I have seen 2 to the power of 16, which is, anyway, it's bigger than 2 to the power of 5. It's not the biggest, but it's way better than 2 to the power of 5 only. This is good and this is good. However, I remember that even in I-type, I need to store the result in the destination register, and I don't have a destination register anymore because I'm using the field here. So what should I do? Well, what I used to use as the second source in the R-type, well, now I'm going to use it as a destination. And you can see that even with a fixed number, we still have some kind of flexibility depending on how we divide the different fields of it. And this is true for the jumps as well. You can notice that the opcode has the same number here, and now I'm using 26 bits. This means that I can jump to way far from where I am. Right, floating point, not going to cover, but it's good for you to read them. Right, so here we're talking about, where's my laser pointer? The form of the instructions, right, and the encoding of it. Let's check this out. So imagine that I'm using the regular add here. I need to specify the destination register, the source register, and the second source register. And the action that's happening while I'm adding the source, the content of the first source to this content of the second source, and storing the result in the D. Here you can notice what is the opcode. So the opcode of it is just a bunch of zeros. Hold on a second. there's something weird. If this add has the opcode of 0, and here I have another opcode of 0, and this is an add u. No, even better. This opcode is still the same, and it's an AND. So how would I make the difference between if I'm adding or ANDing? Let's see what changes. So I'm still using destination sources and destination. Here is nothing changing. Oh, I see. So see this field here? Well, it's difference. So remember when I told you theoretically you could have 2 to the power of 6 instructions? Apparently not, because if we're fixing the opcode, we're still using those fields in order to make a difference. Well, especially this one for now. Alright, so an opcode with zeros with that field here will specify the exact operation. So this one differs from that one. If I read this one here, this would be an add. If I read that one here, it will be an AND. But still, if I'm a human being and I'm trying to read the 32 bits here, well, it wouldn't make any sense. I need to decipher it in a way or another. So I'm gonna go and check my 3 bits, my 6 bits here. So it's some kind of R type here happening. And then I need to read that one. So apparently I'm doing an add, and then I need to go and read my RS, RT, and RD, RS, RT, and RD to know where to store it back. So we're storing it back in one of the source registers, and we need to read the contact. Well, it would be way better for us if it were something like that, and fortunately it is something like that. So see here, I'm reading from 0 from S0, right? Whatever the number of S0 is here, that's represented by that. Adding to it the content of 0, which is always 0, as we've seen, and putting the result here. So basically, it feels like I did nothing. But still, we can see that we're happier with that format than this format, because it will take forever to decrypt everything here. So see, this is the ISA that I told you about, and this is the machine code. So if we're looking at it from the hardware, we're gonna see machine code, and if we're looking at it from software, we'll see ISA. Yep, I haven't lied to you, not yet. Anyways, right, so I'm gonna end up this video with a couple of principles when it comes to RISC, because someone might have read RISC when I was talking about the previous slides. So what is RISC? Well, RISC stands for Reduced Instruction Set Computers. So reduced as in few number. And we have a couple of principles here in order to understand why people came up with that philosophy, the RISC philosophy. So simple is regular. If you fix the size of instructions, which is regular and simple, right? And the number of registers that you're going to use for the operands, so everything is where it's supposed to be. So it's very regular. It's simple to understand and to deal with. Smaller is faster. Should I say why? I shouldn't. You already know why smaller is faster. Because if I want to reach something, well, I have to reach one of those 32 registers. If I had 10,000 registers, it would take me more time to reach the register number 10,000, for instance. Fair enough? And another very important philosophy here is to make the common case fast. And we're going to cover that when I'm going to talk about procedures, hence functions. But just, the common case fast could be also seen as the register 0 that contains the value 0. And engineering is all about good compromises. So, we would have a fixed size, but then again we need to redistribute the fields within this fixed size in order to have different types of instructions. R type, I type and the jumps, for instance, and we need to reach more. So basically we need to be careful how to divide the fields. Alright, let's see now for the CISC. So the RISC philosophy, which is reduced instruction set computers, and the CISC now, we traded the R for the C. So let's see what the C might be. C stands for complex. And here the philosophy is one single instruction. A single instruction here would be able to do a load, some operation, and then store back to memory, right? So this could present a lot of advantages. However, it could have some disadvantages as well, and a lot of them, by the way. Let's pause the video for a second and think about them. Right. So first advantage would be maybe because we have many things done in a single instruction here. It would be more compact code for sure. It would be also closer to the higher languages, so there would be a direct mapping, and fewer calls to main memory, because with a single instruction here I'll be doing a load and store, so I don't have different instructions for that. And finally, well, I need less RAM, less memory, main memory. How come? That's a good question for an exam. Should I answer it now? Let's see. Alright, so less needed. How come? So let's see. No. Yes. So smaller programs. So remember, main memory is divided into data and instructions. So if I need a smaller number of instructions to do the same thing, so I have more space for my data. And if I don't need that much data, space for that data, right, I can use a smaller memory. Yep. What about the disadvantages now? Well, think about it for a second. Oh, I shouldn't have done that. So you see, it does a lot of stuff, and the size might be variable, and it is variable. So basically, we'll spend a lot of time trying to comprehend what is needed. What should I do when I see an instruction like that? Where's my pointer? So we have some overhead, and overhead, hence it will slow down execution. Well, I was happy about that. Now I'm unhappy about that. The chips themselves, designing them is complex, because see, here it feels that we're closer to the higher level language than the hardware itself. So basically, with the RISC, the ISA is definitely the code, the machine code, and you can see that there's almost a direct map. There is a direct mapping between them. Although here, it's not a direct mapping anymore. It feels more like a pseudocode if we transform it into ISA. So yeah, designing the chips is more complex in order to be able to fit whatever those instructions are trying to make or to do. And yeah, if I'm using a lot of stuff, so I'm gonna use a lot of temp registers. If I'm using a lot of temp registers, this means that I'm not using my registers efficiently, because with RISC I know exactly which registers to use and which register not to use. Here, because I'm doing a lot of stuff, so I need some intermediate steps. So that's a bummer. Higher power consumption. Wow. Why would it be? Why? Well, let's think about it. So if I'm spending more time checking the overhead, slowing down the execution, so I have some extra execution power on the CPU, so this will consume energy, right? Forget about that one. Harder to use registers efficiently. So I'm using registers, a lot of temp registers, so a bunch of ones and zeros that I'm changing from time to time, and each time I'm changing the values of the registers while I'm consuming power to do so, right? To flip 1 to 0 and 0 to 1. And cherry on the top, apparently people have discovered that approximately only 20% of the available instructions, because they're very complex instructions, are actually used in a typical program. So 80% are never used. So let's think about it. Which philosophy won after all, the RISC or the CISC? Well, today, almost everywhere, well, it's RISC. CISC is so old school, and no one is using it. You can see some of the companies claiming that their ISA is CISC, however it's a RISC ISA in disguise, it's not really a CISC. Right, so last slide here, you can see the different versions of the MIPS and the implementation of the processor. So what you're looking at here are implementations, fair enough. And here are the ISAs. And yeah, in real life, they used them for my fellow gamers. So they used it as the processors in those consoles here. And the latest MIPS release is number 6, and it dates from 2014. Alright, so 1985. I was born, you were not born. And here is MIPS 3234. By the way, what would be the 32 and 34? Think about it for a second before shutting down the whole video and computer. Well, this is whether we're dealing with words of 32 bits or we're dealing with double words or words of 64 bits. But I mean, let's stick that a word is 32 bits and 64 hands is a double word. Alright, so see you next time.